All right, so welcome back. We're going to continue today on functions and methods in both C and Java, but today we're going to more focus on C because pretty much it's straightforward in Java. What we're going to be looking at today is we're going to start introducing pointers and pass by reference versus pass by value, which is something that is not found in Java. In fact, it's not found in many programming languages. C is kind of unique in that regard, but we'll take a look at what that means here in a second. All right. So remember that we are on YouTube streaming and that we are on Piazza. If you've got a question, make sure that you're posting that to Piazza. All right. So to continue from last time, though, I just want to give us a quick review here of modularity in C. Remember that we did these round utilities. And we separated them out into a header file and a source file. A header file ends in .h, and it only contains the documentation and the prototypes. Prototypes are not the definitions. The prototypes are just the signatures of those functions. And then over here in the source file, of course, we included any libraries that we actually needed, for example, round. And then math.utils, we also included that, but we used double quotes instead of the langle-wrangle. That is just the convention. Here's why we do that. Basically, if you use langle-wrangle, that tells the compiler, look for this library in the standard spot, or wherever all the standard libraries are located. If you don't find it there, then go looking for it in the user-defined spot. The double quotes here shortcuts that and says, don't bother looking for this because in the standard library spot, because it's not a standard library, it's a user-defined library. So just immediately look in the current working directory or wherever else it should be, right? So by convention, we use the double quotes for user-defined libraries. Otherwise, we have the definitions, which repeats the signature and then provides a function body of what that function does, okay? All right, so and then over here in the demo, we of course included anything that we needed. This is not necessary, of course, because we're not using the math library anymore directly. Our library uses the math library. We're just using that library, right? So we include the header file here as well. To compile all this stuff, it's a multi-step process. Yeah, go ahead, question. Right, definition in the .c file, source file.
But you linked both, like the little direct, or like the demo.c and the round utils.c to the .h file.
So the
.h file is just like the signatures.
The .h file is just the prototypes, prototypes and documentation, of course, by convention.
All right.
Right. And this is, and the source file, the .c file, is all definitions. Okay, and some other things, but we'll get to those later. But we haven't introduced those yet. So the way that we bring all these things together is, first of all, I need to compile my library, just like the standard input-output library. It's already pre-compiled and on my system. Somebody at some point compiled that by using GCC or some other compiler, and just simply compiled it -c roundutils.c. Right? And it did not produce an executable. Over here, you'll note that it only produced this .o file, which is an object file. If I, in fact, ask what that is, it says that it's this relocatable x86, that's the processor, 64-bit processor, version 1, blah, blah, blah. It is just an object file. All right? It is not something that you can run. If I try to run it, round utils, it won't even code complete it because it's not a runnable file. Permission denied, right? So now that I've got this library sitting here in the current working directory as an object file, I can compile everything together, link them together, and produce an executable file. GCC, if I just do this, demo.c, then I get an error message that says, I have no idea what round descents is. Actually, I do know what it is, because I know what its signature is, but I don't know the definition because you've not linked in the library. Just like -lm is necessary to link in the math library, we have to provide that .o file. So GCC roundutils.o and demo.c. And we get the exact same error message as before because we have not used the -lm. -lm is akin to providing this object file directly from the command line. When I do that, now I finally have that executable there. Right? And I've got round to cents here. It's rounding $123.45.6 to $123.46. Okay? All right, so that was a little bit of a review from last time. Again, this can get quite complicated, and I mentioned it at the end of last time that if you really want to do this stuff, and if you've got a larger project and you've got hundreds of files, you don't want to sit there and type this every single time. In fact, you might not want to do that with your homework. So instead you use a utility called make, and you use a make file. I posted a tutorial for CMake, which is a modernized version of make. If you can go ahead and use that as well. It's cross-platform. But otherwise, just take a make file and reverse engineer it. For everything that you're going to do in this class, it's just simple stuff. Okay? For Java, you've got several build systems to choose from. Ant, Maven, Jenkins CI, which is a continuous integration tool. Lots of fancy bells and whistles and stuff. We're going to keep it simple because we're just introducing coding. If you want to get into this kind of stuff, this is called DevOps, development operations, right? Where the last job I had outside of the university was we had 2 people completely dedicated to doing nothing more than writing build and deployment scripts. It was 2 full-time jobs just writing the scripts to build stuff and push it out. So it can get quite complicated. A system can get quite complicated enough that you need that kind of those tools, and you need people to build and maintain those kind of tools. What I want to do, though, is today I want to discuss a little bit more detail of how do functions actually work. Okay. So programs, your executable programs, have what is called a program stack, right? Or call stack, right? Sometimes they're called call stacks because you're calling functions, so they just call them call stacks sometimes. All right, what is a stack? A stack is a LIFO data structure. So what is LIFO? LIFO is last in, first out. Imagine a stack of dishes, or a stack of pancakes, I prefer. But you've got a stack of dishes. How do you operate, or how do you interact with this stack of dishes? If you want a dish because you want to go and eat those pancakes, what do? You take one off the top. Do you take one off the bottom of the stack of dishes? No, what's going to happen then? Wobble, 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 fall over, break, right? So once you've cleaned your dish, and you're in the cafeteria or whatever, what do you do with it? Do you want to put the dish on the stack of clean dishes so that other people can take it? Do you put it in the center, or do you put it at the bottom? Well, I mean, if you're screwing around, maybe, yes, but normally you put it on the top. So the last dish that you put on the top is the first one to come off the top. And that's why we call it LIFO. Those 2 operations are called push and pop. Push, you insert an element at the top of the stack. And I'm putting that in double quotes there because conceptually there's a top because of our visualization, but it doesn't really matter. There's a stack inside the computer. You take the computer and you turn it upside down. The dishes aren't going to fall, right? It's just a way to visualize things. And pop, you retrieve and remove an element at the top of the stack. This is really, really nice because it leads to what are called breadcrumbs, right? A stack can be used to keep track of breadcrumbs. Right? This term comes from Hansel and Gretel. How do you keep track of where you've been? Hansel and Gretel are led into the forest to get lost by their evil stepmother or whatever, right? And they understand we need to find our way back. So we take a piece of bread and we start putting breadcrumbs to the trail that we're taking, so that when we're finally abandoned, we can turn around and we can follow those breadcrumbs back out of the forest. Unfortunately, of course, breadcrumbs, being nice and delicious, they were eaten. But what we're going to be putting on our stack are not nice and delicious, so they're not going to be eaten. But it's a way that you can keep track of where you've been. And in the context of a program stack, that means that it's keeping track of all the function calls. Each time a function is called, a new, what's called a stack frame, is created, on top of the call stack, right? Each time a function returns, the stack frame is popped, created and pushed, I should say, because we want to use those terms. Get used to using those terms pushed and popped. By the way, why do we call it pushing when you're just setting it on the top? Think about the cafeteria with the actual dishes. Are they stacking those dishes really, really high? Or they put it on the top and they push it down because it's spring-loaded, right? And that's where we get that's literally where we get the term. They needed a term for it, and they of course looked at the cafeteria way. We're pushing the dishes on the top. Okay, we'll go ahead and do that. I have no idea where pop came from though. We pop it off the top. Maybe I don't, pop your tops or something like that, and they just took that term. But each time a function returns, the stack frame is popped off the top. Right? This is great because it keeps track of where we've been. When a function is called, how do we get back to where we were in the code? Well, it's just the program stack. Not only that, but each stack frame keeps track of local variables, right? Parameter variables, and return values. Right? So everything that you would need in a function as far as variables go are contained in those stack frames. So what I'm going to do is I'm going to give you an example here, a couple of examples. Let's go ahead and just take a look at this code right here. This is C code, but this works as the same in all programming languages, Java included. So you're not losing anything here by looking at just C code. Now, this is terrible code. Never write code like this. This is just for demonstration purposes. If you want to compute the average of two numbers, simply just add them together and divide by 2. You would never actually write a function to sum two numbers together. You would never actually write a function to average two numbers together. I just want to show you how this works, okay? So what we've got here in the main is we've got two numbers, n and m, 10 and 16. We call this function over here called average, passing those values in as inputs, 10 and 16, parameters. Over here, the average takes those in and renames them, right, a and b. Then it calls the sum function, which takes a and b as well, and then adds them together and returns that value. Right? The visualization looks something like this. When a program starts up, of course you've got the program code itself. That's at the bottom of the stack. Then you've got global variables, static content like hard-coded strings and other hard-coded values and stuff like that. That's going to be in the global variables and static content. Then what's the very first function that actually gets called that kicks everything off? Main. And in this case, we've got n, m, ave. Those are all local variables that are inside this stack frame. This entire thing right here in green, in a different shade of green, is the stack frame. Right? We've also got the return address, 0, and we've also got the arguments or the parameters. Remember, every main does have parameters, argc and argv. Those are contained in the stack frame for that function. When main calls average, then a new stack frame is created on top, right? And we've got a local variable here, y, right? It's also our return address, which is going to end up being 13, return address value, however you want to look at it. And we've also got arguments, a and b. At this point, I will draw your attention. Are these the same variables as n and m over here? No, they exist in completely different stack frames. This is how we're able to have variables of the same name in different functions, because they exist in different scopes. They exist in different stack frames, okay? Likewise, when average calls sum, then we pass in AB. These are not the same AB as these down here. They are effectively copies, right? We also have the return value here, 26, that's 10 plus 16. The arguments a, b, and then the local variable x that we created here to hold that value. Now, this is unused stack space, of course. Here's a preview of something that we're going to look at later on when we look at recursion, where you've got function calling, function calling, function calling, function. If you start stacking dishes up too much, what eventually happens? It'll all fall over, right? This is a stack. A stack is a very limited amount of memory. In fact, on CSE, I think that the limitation, the standard Unix or Linux limitation is 4 megabytes. So if you've got function, calling function, calling function, calling function, calling function, eventually you run out of stack space. You put one more dish on top, right? And that's the straw that broke the camel's back, right? And it all falls over. You put one more stack frame on top, and what do you have? It's a full stack to begin with. Putting one on top makes it over full, and so therefore what happens when you fill a cup too much with liquid? It overflows, right? The stack has overflown. Sound familiar? Stack overflow, and that's where we get that term, okay? But otherwise, when we return back from these functions, when we return x here, this stack frame gets popped off the top, right? All these local variables, all this return value, all these arguments are gone now. They're effectively deleted. That's how it goes out of scope, right? And that's how we keep track of all these variables and how it allocates new memory for these variables and then deallocates it by popping this off the top. Sum returns to average, average returns to main, and so this one gets popped off the top. Then at the very end of the program, I don't know whether or not the main stack gets popped off, but or if it just the entire stack here gets cleaned up by the operating system at the end. Okay. Pretty cool mechanism because it virtually requires no thoughts at all. You just create a new stack, create a new stack, create a new stack. It's as simple as can be. You use the LIFO order, and you're good to go. One consequence, however, of this is you can't do certain things. So what I mean by that is what I want to do is create a function to swap two variables. Right? This is another tool that I often use. It's a visualizer. It'll actually visualize your code. For simple stuff, it's okay, but it's a good teaching tool. It's not a good tool to use in practice. So, but I do like it here for today because it does demonstrate what I want. So what I want to do is I want to write a function that will swap values. Oops, I don't want to save. So I've got x and y here, 10 and 20. I print them out, and of course it would print out 10 and 20. I want to call this function that I'm about to write swap. And when I get back from it, I should expect 10 and 20 have been swapped, right? Okay, that's my goal. So help me to write that code. I've got a and b. I'll put a over here into a temporary variable on top of the table. Int temp is equal to a. Right? Now a is free over here. I can put b into a. A is equal to b. Right? Now I take that back off the table and put it over here into b. B is equal to temp. Right? And then I'll return. It's a void function. You're asking when do we use void functions? Here, right? We're not returning anything. We're just doing something. Yeah, go ahead.
Shouldn't you put like what's it called, like a prototype or something?
Oh, good point. Do we have to have a prototype? Strictly speaking, if I put the definition up here, no. But it is best practice. This is just a quick demonstration to put the definition down here and then the prototype up here. Yes, that's a better way of doing it. I'm just doing a quick and dirty demo to show you that this actually ain't going to work anyway. All right, let's visualize this. Don't think I have any syntax errors here, but sometimes it's slow. So I'm going to walk through this code now. And over here, you'll see the output, and hey, what's that? There's the program stack. We've got a main here, which has argc, argv, x, and y. If I step through this, step, you see that a couple things happen here. First of all, there were no arguments. Well, there was one argument, which was the executable file name. There were no argument vectors, and so what this tool uses is the poop emoji here for uninitialized pointers. We'll talk about that in a second here. And then on 14 and 15, I've assigned the values 10 and 20. Now we're about to print them out. We do, and you can see the output up here, 10 and 20. Now what I'm going to do is I'm going to call this function swap. Right? Are x and y the same variables as a and b? No, that's why I intentionally named them something else, so that you understand that they're completely different variables in a completely different stack frame here. When I start the function, they receive 10 and 20, copies of the values of the variables. When I swap A and B on lines 7 through 9, is that going to affect X and Y? Nope. It's just going to take A and put it into temp. It's going to take B and put it into A. It's going to take temp and put it back into B. A and B are certainly swapped. If I were to print them out in this function, you would see 20 and 10, right? Because that's what they are. But when I return back from the function and the stack frame is destroyed, A and B no longer even exist. X and Y are still 10 and 20, right? And when I print them out, you see that they're still 10 and 20. So as a consequence, I'm not able, because of how functions work, I'm not able to do something like swapping, right? So observations of what we just saw. Consequence is that every stack frames variables are separate, right? This is how function scoping works, right? And it's a very, very good thing. Every function gets its own scope and its own stack frame, right? Its own variables. It doesn't matter if you called them the same thing, X and Y, A and B, doesn't matter. They're completely different variables. In most programming languages, variables are passed by value, right? And that's what I was just getting at with this demonstration. The value of the variables are copied into the parameter variables. The original variables are completely different, right? Only copies of the values are given to the function, or not, I'll use the proper terminology here, passed to the function, right? So this is same in Java. By default, everything is passed by, well, Java's a little bit weird, but for the most part, passed by value for now, okay? That copies of the values are exchanged. We'll get into the nuances with Java here by the end of the day, okay? Sometimes you do want to pass the variables instead of their values, right? This is known as passing by reference, right? And it's supported in some programming languages. In particular, it's C. It's the de facto way of doing things, and it's how we're going to end up doing things going forward. But first of all, we need another concept here as far as C is concerned. You need the concept of pointers, okay? So to understand this, you need to understand a little bit of memory and how memory works in a computer. Every piece of data in a computer is stored in memory. And when we say memory, we mean a lot of things. There's an entire memory hierarchy. There's memory on the actual processor chip, right? That's the processor memory. Then there's main memory, right? If you buy a DIMM or can you buy SIMs anymore? Nobody sells SIMs. Single inline memory chips, right? They're going to be double like chips on both sides, so that you have double the capacity basically. I asked it yesterday what the standard is now usually for like a desktop, and somebody said 16 gigs. Is that correct? Is that?
It still depends. I mean, in most situations, 8 would still work. But
okay, for the most part, 8 gigs. I have no idea what I have on this laptop, but it's 5 years old. Go ahead and humble brag. What have you got on your laptops? 16 gigs? You don't know? Oh, okay. All right. Any idea? 16, okay. So 16 gigs, right? That's the main memory. But you also, on top of that, you have what's called virtual memory, right? Where the operating system is actually keeping track of a lot more stuff than it can hold in main memory. What it does is it uses disk to copy that. And so you've got this whole memory hierarchy where you want to minimize the amount of thrashing between all those, between that hierarchy. But at the end of the day, it doesn't matter. Everything is stored in memory, right? Memory consists of both an address, That is its location of where it's actually stored in memory, and contents, right? The data actually stored, right? So here's a really quick visualization over here. Ignore this picture over here. Here we've got an address and we've got contents. The addresses are usually just some hexadecimal number, right? Just like, physical addresses are just a number. They're organized numbers, so that, 1060 West Addison, and then we've got 1062 West Addison, and then 1064 West Addison, right? They go in order. Evens are on one side of the street, odds are on the other side of the street. It's just a way of organizing stuff. Memory is usually byte addressable, so that you can get access to every single byte. And then to get access to an actual bit, a byte is 4 bits. To get access to an individual bit, of course, you'd have to do what's called bit twiddling, where you get the entire byte, and then you just pull out that 1 bit if you needed to. But otherwise, memory is usually byte addressable, okay? And so if you want to access something, you need to know where it's stored, and then if you want to visit your friend, you need to know where do they live, so that I can go to their address, and then I can visit them in their home, find them in their home, right? And that's like that's what data is. It's stored at a memory location, a memory address, and then the actual contents are stored at that cell of memory, right? In C, you can create a pointer variable that represents not the data, but the address, the memory address, where the data is stored. And by data, I just simply mean, well, an integer, a double, whatever you want, right? To create a pointer variable, you use the star operator, or star symbol. It's not an operator in this sense here. All right, so here, I'll go into code mode here, and we'll look at a visualization here in a second. But here's a normal, regular old variable. Int a equals 42. Right? That's just a regular old piece of data, okay? Where is a stored? Well, I don't know, but the program knows, the operating system knows. Up till now, I haven't really cared, right? But now what I want to do is I want to have a variable that actually points to that memory location. And we call them pointers because they literally point to a memory location. That here it is stored in memory. We're going to point to that memory location, right? And that's why we call them pointers, right? Here's a pointer variable declaration. Int ptr to a. And ptr here is just short for pointer, right? All I'm doing here is adding a star in front of my variable. It's not a regular old integer, int, variable name. It is an integer pointer, int star pointer, right? So at this point, ptr to a is a pointer variable that can point to any memory location that holds an integer, right? Usually 4 bytes. Usually. Not necessarily though, right? Usually 4 bytes. In general, it is best practice to initialize your pointer to point to something, right? If you know what you want to point it to, do it. If not, then at least point it to null. All caps, N-U-L-L. So we've got yet another concept of nothing, okay? 0 is a numerical nothing. An empty string is an absence of characters, right? Void is a function that returns nothing. Or void is a function that takes nothing if it's a parameter void, right? In this case, though, this is a nothingness with respect to memory locations, okay? All these nothings are not created equal. All of them are used in different contexts. So don't mistake 0 for null. At a lower level, it can kind of be that way, and you can kind of hackishly do that, but don't use 0 as a placeholder for null. It's bad practice, right? And it can get you in trouble later on. So null is the null pointer, right? It doesn't point to anything. Right? It points to nothing more. Sometimes we use dev null, if you've ever heard of that term before. Unix systems will usually have this black hole that you can redirect stuff, ls dev null, right? And there it is. It's just an empty file that anything you write to is thrown away, right? And so you can always say, complaints will be sent to dev null, right? And it's a hacker joke that complaints will be ignored, right? So everything that ends up in null is gone and lost forever, right? It's like a black hole that you can throw your garbage into and not have to worry ever about it again, right? Wish we had something like that, right? But it's best to point it to null. If you don't, you have what is called an uninitialized pointer, right? So it could point to anything, right? It could point to an invalid or non-existent memory location. It could point to a memory location that exists but doesn't belong to you. It could point to your own memory location that does belong to you, but you risk corrupting your own memory. Right? So these are three bad things that could happen, right? First of all, it could not exist, right? If you only have 4 gigs and you try to address something that goes way beyond that as far as addressing goes, then it doesn't exist. If you try to, usually they start at 0 and they go up. And so if you try to address a negative memory location, then that doesn't exist. If it points to a memory location that does exist but belongs to another program, imagine how you could exploit that. Right? Imagine if you were able to access arbitrary locations in memory. And if you could locate the memory location that, say, cryptographic keys or passwords were stored, right? Now you can write a very simple program to start hacking and gaining memory access that doesn't belong to you. Usually a good operating system will detect that and say, no, illegal, you can't access that segment of memory because it doesn't belong to you. So I'm going to kill your program with a segmentation fault. You've probably seen this before if you forget an ampersand somewhere with printf or with scanf. That's what segmentation fault means. You faulted out of your segment of memory into somebody else's memory, and somebody else's as in some other program's memory. And it's going to kill your program. Hopefully it kills your program, right? If it doesn't, then that's a security flaw that can be exploited, right? Otherwise, if you could be pointing to your own segment of memory, and so you can do whatever you want with it, right? The operating system is going to say, here's your memory, you can do whatever you want with it, right? Remember, C is a programming language that if you want to shoot yourself in the foot, it's just going to ask you what caliber you want. It's okay with you corrupting your own memory, right? It's okay with you rewriting your own code on the fly, right? It doesn't care. With great power comes great responsibility. You need to make sure that you're not corrupting your own memory, right? So following good practice and not having uninitialized pointers, okay? Otherwise, again, the visualizer over here, this is an uninitialized pointer. It's visualizing that as a poop emoji, right? It's garbage, right? I don't know if there is a garbage emoji that's more appropriate than a poop emoji, but that's what they chose to do, right? Is there a garbage emoji, anyone? I don't know, what would it look like? A garbage bin or a trash can? Okay. Yeah, go ahead, question.
So what exactly do the pointers do again? Like, what does it mean to point?
It means it's pointing to a memory location. So I'll show you another visualization here in a second, but if I've got a pointer and I make it point to a memory location, that means that its contents are actually the address of another memory location. Instead of, say, 10. Like a regular old variable would hold the value 10. Over here, this holds a memory location, memory address instead. Okay? So back to over here, how do we do this? How do we point it to a proper memory location? So we'll initialize our pointer to null. And that's simply just ptr to a is equal to null. Oh, ptr to a, excuse me. All right. You could just make it equal to null, and you're initializing it to null. Yeah, this is not too useful. If we know that we want it to point to A, if you want it to point to a valid memory location, you need to get the variable's address. Right? So how do we do that? If I've got int x, or a, is a regular old variable. Right? To get its memory location, you use the ampersand operator. Right? This is the referencing operator. There we go. Right? So for example, I will go into code mode here again, and what I'll do is I'll make ptr to a point to A's memory location. Right? And to do that, ptr to A, instead of making it equal to null, I will make it equal to ampersand A. Right? Ampersand A, putting the ampersand in front of a regular old variable gives you the memory address of that variable. Right? So putting an ampersand in front of a regular old variable gives you the memory address of that variable. Right? And that's how we can make pointers point to things. Further, you can now manipulate the contents of a variable through its pointer. Right? So if I've got an integer variable a and I set it equal to 42, I can always reset that to 5, right? Just by using the assignment operator. Right? So let's go ahead and do that. I'll do int a is equal to 42. I can reset a. How? Well, a is now equal to, I don't know, 17. Right? I can change the values directly. Otherwise, I can do it through a pointer. So again, make a ptr to a point to a, and the way that I do that is int star ptr to a is equal to ampersand a. And now what I can do is I can change the contents of a via its pointer. And the way that I do that is through the dereferencing operator. ptr to a is equal to now, I don't know, give me another number. 30, okay, all right. There we go, 30. Right? Note what I did here. I put another star in front of it. That's the dereferencing operator. Oops, sorry. The star operator is the dereferencing operator, right? So these are kind of like antonyms of each other. They're kind of complements of each other. If I want the memory address of something, I use ampersand. If I want to take a pointer and turn it into a regular old variable, I can use the dereferencing operator, the star, right? Don't ask me why that's star. Don't ask me why it's ampersand. It is what it is. Don't ask me why you use a star and then also a star to dereference it. It is what it is. Right? You'd have to go and ask Kernighan and Ritchie why they chose those symbols. There might have been some reasoning. But there we go. That's good. That's good. Right? That's good. Okay. So let's see this in action. I'm going to go ahead and go through this visualization tool again. Edit this code. We can get rid of this, and we can get rid of all of this, and put that in. Of course, I don't have good indentation here. That's fine. I just want to visualize what this looks like. There. Ignore argc, argv. Those are not relevant. We've got a regular old integer a, and we set it initially to 42. Of course, you can just go ahead and directly change its content, 17. I create a pointer variable here, and I make it point to a. Right? And you see that little pointer right there. It doesn't hold a value. It holds a memory address, and it's referencing this thing up here. Right? And if I could resize this No, you know, if they, of course, you would see a nice, you know, winding little arrow if I had multiple stack frames here, which we will in a second here. But otherwise, PTR to A is pointing to this variable. When I set it to 30, I dereference it. Dereferencing means that I go from the pointer, I jump to that memory location, and then I change the contents of that memory cell to 30. Right? And that's how pointers work. Why would you ever want to do this? I can change it to 17, right? Well, it solves the problem from before. Let me go ahead and back up to what I had before. Here's my main. Get rid of this. I do want to swap something, right? To do that, I have void swap integers A and B. Int A, int B. Before, when I did it like this, I was passing copies of the values. What I can now do with pointers is I can pass in memory locations instead. Pass in a memory location, pass in a pointer to an integer. And now I can swap them. Int temp is equal to A, int A is equal to B, and B is equal to A. Is that the way of doing it though? Return. This is a regular old variable. Temp is a regular old integer variable. Is A a regular old variable? Nope. It is a pointer. How do I take a pointer and turn it into a regular old variable so that I can jump to that memory location and grab that 10 out of there? I dereference it. Likewise, when I put something back into that memory location, I need to dereference it. I need to jump to that memory location. I like to call these things buckets. Oh, not A, but temp. There we go. That fixed it. Oh, should I dereference temp? No, temp is not a pointer variable. There's no point in dereferencing it because it's not a pointer, right? So yeah, go ahead.
Use the asterisk to make it like a pointer.
Yep, this is A is now a pointer. A and B are now pointers. So I'm passing memory locations to you instead.
Right. And then it points to X and Y respectively.
Well, we'll take care of that in a second.
And then you like put the asterisk in front of the A again, like later on in the
The asterisk here dereferences it.
the value.
Right. So again, I like the analogy of buckets. If I gave you copies of my variable, I've got 10 and 20 here. I copy them and I gave you copies of them. I still have my original 10 and 20 over here. Right? There's no way that you can manipulate your variables and I can see that manipulation over here of the swapping. So what I'm doing here by giving you pointers is I'm sharing a bucket with you, 2 buckets. In the first bucket is 10, and the second bucket is 20. I'm giving you the buckets so that you can take those things out of the buckets, swap them, and we still have, and you give me the buckets back, basically. Right? So that's a way that I can pass a variable rather than a variable's value to you. I'm passing a reference, I'm passing a pointer. This is passing by reference now. Now this is still not going to work because is X a regular old variable? Is X a pointer variable so that it can be received as a pointer variable up here? Nope. How do I take a regular old variable and make it into a pointer variable? Ampersand. And ampersand. Now let's visualize this. Yeah, go ahead.
Why don't you do that for A and B at the top?
Because they're already pointer variables. If it's a pointer variable and you want it to transform it back into a regular variable, you're dereferencing it. If you have a regular variable and you want to transfer it into a pointer variable, you need to reference it. So ampersand, star, they're opposites of each other. Right? They take it back and forth, literally. Right? All right? So next, print 10 and 20. Over here, though, when I call swap, a new stack frame, and these are pointer variables, they're no longer just regular old variables. They are buckets that point to these guys up here. A points to X, and B points to Y. So that when I go to this bucket, I dereference A, I'm jumping to this memory location so that I can grab the value 10 and put it over here into temp. Right? Then, on the next line, When I dereference A, I'm jumping to that memory location. I dereference B, jumping to that memory location so that I can actually swap them. Right now it's 20 and 20. And then the last one, I dereference B so that I can put in the temporary value there. And you see now that 20 and 10 are now swapped. And so when I return and that stack frame is destroyed, only the pointers are destroyed. The copies of the variables, I never copied them. I gave you the memory locations instead. Right? And now it's successfully swapped, 20 and 10. Cool. This is kind of a toy example because you would never actually just write a swap function. You would just do something like this directly if you ever actually wanted to swap something. But it shows you the possibilities. Right? And how are we going to be able to exploit this from now on? Right? This opens up a whole new world. We can now do arrays. We can now do strings. We can now, passing by reference now means that we can return multiple values. Right? Before a function, in fact, still a function only returns one value. Well, how can I return, say, 2 values or 3 values or 4 values? I can give you 4 buckets, right? And you can fill those buckets with various values, and then I can return those values. We're not actually returning anything, but I still have those 4 buckets in my hand. Now, one function can compute multiple values. Right? You can also do well, we'll get to more later on. But now, well, actually, no, this is what I wanted to say. Now that we're doing all this through pass by reference, that means that the return type, say an integer or a double or whatever, we don't have to use that anymore. Right? Make that a void. Well, now we can actually use this for something. Right? If we're not using that for a return type or return value, we can actually use this for an error code. And now we can do error handling. Right? This opens up a wide possibilities in C of doing everything else. Right? Error handling, arrays, strings, et cetera, et cetera. Right? So it's only possible through pointers. What I want to do now is talk a little bit about Java before we move on, right? Actually, let's go back to the notes here first, all right? Java, Java, right? Obviously, Java has no pointers, right? You do not generally, unless you're going to hack the Java virtual machine or something, directly manipulate memory contents. Right? By default, it's just the fact, I guess. By default, all primitive types in Java are passed by value. In other words, primitive types like int, double, right, char, etc. Anything with a lowercase beginning letter is a primitive type. It's a built-in type. Okay. Otherwise, all reference values, say string, right? Integer, the capital values of integer and double, etc., right, are passed by reference, but, right, generally, generally, built-in types are immutable. What I mean by immutable is once they're created, they cannot be changed. So even though I'm giving you a pointer, right? I'm giving you a reference to this integer 10 and this integer 10, right? If you try to swap them, all you're doing is swapping the reference rather than the values themselves, because once this integer 10 is created, once this integer 20 is created, you cannot change them. Reassigning a value creates a brand new integer with a different value. So I want to demonstrate that to you, and I'm interested to see what the visualization looks like here. I'll go ahead and go with a capital I integer here, just to show you. Otherwise, it's just straightforward. It's always going to be passed by value if they're primitive types. Integer, x and y is equal to 20. Print them out, system.out.printf, or println x plus star y, there we go. I'll just keep it simple. And then we'll go ahead and swap x and y, okay? Let's write that function, or let's try to write that function. Public static void, swap, integer a, and I'll even use the same naming convention here, a and b, to really drive home the point that those are actually different reference variables, okay? They're not different primitive types. They are references, but they are copies of references. So hopefully the visualization will demonstrate this. So integer temp is equal to a is equal, or b is equal, or sorry, a is equal to b, and then b is equal to temp, right? And then return. I'm really interested to see what this looks like. Ah, what? Main server is, oh, no, there, okay, there, finally, it did work. It complained, but then it worked, right? So I've got main over here, x, y, and print. Right? Oh, print, one more step to print it. There we go, all right? So 20 and 10. Now when we create a new stack frame, we've got A and B, which are different, so it's showing, it's gonna visualize this as receiving copies of those things, and it's probably actually how it's working under the hood. And those copies are going to end up being swapped, right? Same thing would happen with a string, I'm sure. There's a void value, so let's edit this code. Let's swap strings instead. There. And string x, and 10, and 20, right? Let's visualize that execution. Probably going to end up being the same thing. Oh, draw pointers as arrows. Well, there are no pointers in Java, so it's not going to draw them. I really wish it had drawn them so that it could show you that that it in fact is doing something weird, but it's doing something similar to C, but not exactly the same thing as C. Right? 10 and 20, they received those values, and they ended up getting swapped. All right. So basically, for all intents and purposes, at the end of the day, it's passed by value. Say what? It's not X and Y, no. I'm sure that they're pointing to the same memory location. It's just that you can't change it because it's something completely different. Let me try to show you one more visualization of this. Foo is equal to hello, right? Now, if I try to change foo, hello, I'm not changing the contents of it, okay? So I know how to, now I know how to show you this visualization. String bar is equal to foo, right? And then I will change foo into hello. Not var, bar is what I wanted. There we go. No save. How many strings are there here in memory? 2, right? Foo is pointing to hello. We make bar refer to foo, so it receives this lowercase hello. Goodbye. Just really, otherwise, caps is not enough of a difference here. Foo is simply being reassigned to point to something else. Let's visualize that execution. And you'll see that there are actually 2 strings in memory. Foo is not changed on line 8. Instead, foo, bar, completely different strings. So that when foo is going to end up pointing to a new string called goodbye. The old string here, which was unchanged, it's immutable. You cannot change it, right? And that's what happens in Java, right? It's a consequence of immutability. And by the way, immutability is a very good thing, right? All trademark cap there, right? Very good thing. Why? Because you get concurrency safety, thread safety for free, right? So again, let me ask you about your laptops. Does anybody can you even buy a single core processor anymore? I don't think so, right? So I think I've got 4 quad core on this computer, even though it's 5 years old. I've got a quad core with hyper-threading. I've got double that. I don't think they do hyper-threading anymore. I'm not sure. They do? Okay. On Macs even? Okay. I have no idea. What are your processors? Quads? Or does anybody have the Ocho yet? There you go. So six cores, do they have 8 cores yet?
Yeah, they, like the Ryzen, that's what I've got on my desktop.
Okay, do they call them ochos? They should.
I don't remember what they call them.
You know, the ocho. But they missed a chance there for a great joke. Anyway, the point is that we live in a hyper-threaded world. We live in multi-threaded computing world now. You can't even buy a computer now that only has, maybe a phone or something like that, that would only have a single processor, right? The Java creators were very, very forward-thinking. They were seeing that in the future, we're going to have way more processing power by using threads and concurrency. In other words, we're going to have multiple processes running at once. You can't have each one of those processes stepping on each other's toes. If you have a piece of data where process 1 and process 2 are both accessing that data, you have to have thread safety of some type. Where you block this other thread over here while this thread works, and then once this done, then you unblock it and this one takes over. Well, if you're doing that over and over, that means that only one thread can ever work at once, defeating the purpose of having multiple threads. So one way of solving that is by making everything immutable. Now, this can read it, but you're guaranteed that neither thread can change it. This thread will not be able to pull the rug out from this thread over here. Awesome. Thread safety essentially for free. And that's why immutability is a very good thing. And so, in fact, some languages, some functional programming languages, they eschew variables altogether. Or everything is immutable, right? Where you can't change any. Once it's created, you can never change it ever again. If you want a different value, then you have to create a new variable, right? And that's how some languages work by default. In fact, some functional languages, purely functional languages, don't even have variables at all. Right? It's just function call after function call after function call, and you don't even have a variable. Right? There's no variable you can declare and set. Instead, everything is a parameter variable or a return value, and that's it. Right? I did not change. I made foo point to goodbye instead. So here are the pointers. Foo is pointing to hello. I make bar also point to hello. They're pointing to the same thing. Now, when I reset foo over here on line 8, it creates a brand new string over there, and now that's foo is now referring to it. But I'm not changing this one over here.
So instead of food instead of it just being a variable that you can change the value of each variable, is actually just a function.
Exactly. Now, primitive types are different. Int, lowercase I int, that's different. That is a bucket that you can take values out and put new values in. That is mutable. You can change those values. But all the built-in types, string, capital I integer, capital D double, those are all immutable. You cannot change them. Right? If you change them, then you're creating a new instance and making the reference point to that instead. So in that sense, we do have pointers. It's just that we don't use them directly in Java. Right? And again, it is a very, very good thing to have for immutability. Right? So, miscellaneous. Let's see. In C, go back over here. In C, a pointer type must match its the type it points to. Right? For example, the following is wrong. You cannot do, or you can do something like this, but you shouldn't. I can have an integer variable here. Well, here, let's do a double. Pi is equal to 3.14. I'll create an integer variable that, as a pointer, ptr to pi. And I will try to make it point to pi, right? This is wrong, right? You should not have an integer pointer point to a double. And the reason why is that if it's pointing to an integer, it's going to assume that it's pointing to 4 bytes. Where in actuality, it is a double that is 8 bytes. So if you're only pointing to the first memory location, then you're considering the next 4 bytes. not the next 8 bytes. You'll have a type mismatch here, right? So don't do that. Instead, if you want a double pointer, create it. Just create it. Right? So double, how do I create a double pointer? Double star, right? Correct. Pointer to pi. And I can make it point to pi. That will be correct, right? Again, it's not going to catch that usually, and it's going to let you do whatever you want. If you want to point to 4 bytes instead of 8, that's your business, right? That's what the operating system is really blasé. It's going to let you do whatever you want to do, right? Whether or not it's wrong. Recall, scanf, when we use scanf, we used the ampersand. Why? Do you know, understand why we used ampersand? Scanf, percent, I don't know, D, and then A with an ampersand in front of it? Because scanf is a pass-by reference function. The way that it's working is scanf is asking for a bucket. I'll go ahead and read the standard input for you. You need to give me a bucket so that I can put the value in it, so that you can have that bucket back. It's not going to return the value. There is something that scanf returns. It returns the number of tokens that it's matched. It's an integer. So if it doesn't match any tokens, it'll return 0. If there's a 1 token right here, and if it matches, then it'll return 1. Right? It's a way of doing error checking. Remember before we said, or I said, for now, just understand that if you mash the keyboard, it's going to give you 0. Well, now there's a way to check for that. All you have to do is not only give it a bucket and fill the bucket, but when you get the bucket back, you can ask, was the bucket filled or not, by looking at the return value. 1, oh, okay, it found that 1 token. 0, no, it did not find that token. Right? But we're past interactive input at this point, though. But it is important to understand how that worked originally. And I said, for now, ampersand is magic. Now it's no longer magic. Now we know what it is. Right? Let's see. Maybe just a really quick summary here of to change a regular variable into a pointer, right? Memory address. Use the ampersand. To change a pointer variable into a regular old variable, use the star. Right? So they're complements of each other. Okay. Let's see. Want to make sure that I got everything. Yeah, go ahead.
I just don't understand how you do like the pointers and stuff in Java.
You don't. There are no pointers in Java. So a swap function is not even possible. Period. You would have to have a mutable type. So Java mutable integer. There is a mutable integer type. I think it's atomic or no, that's something else. Ignore that. That's commons. Big integer, that's not mutable though. I think it's atomic integer, isn't it? Java atomic integer. Atomic integer, there you go. You can change that. It is thread safe. It's not something you want to use though, unless you're doing some really, really cool multi-threaded programs or something like that. Stay away from it. It's not possible to write a swap function.
So how are we like going to do stuff? Are we going to have stuff like swap functions?
Not in Java, but everything else is achievable through other means, like error handling uses exceptions instead. Arrays, there's still dynamic memory, but you don't have all the bells and whistles that you need in C. One last thing I did want to mention is you can also check for null. In fact, you should in both languages. You know, just having a chunk of memory here, or a chunk of code here. I'll do this in C, right? But you can check for null to see, as long as you've set it to null, you can check for null and then be defensive about it. Don't just dereference a null pointer, because if you dereference a null pointer, then Bret Hart will yell at you. And I don't know if this, here, I'm gonna have to take out my, there we go. Hopefully this is the one I wanted, I think, yeah. Oh no, where's my, no sound here. Okay. Bret Hart, a wrestler from the 80s, he's probably retired. But this was a WWF game that they were developing, and this is a promotional video. And I always like to play this because now that we know pointers, you will always remember never to dereference a null pointer as long as you remember Bret Hart. That if you do dereference a null pointer and you get a segmentation fault, just remember, or just think of Bret Hart standing behind you, slapping your head like that. Again, it's on Canvas. You can go ahead and watch it there. But otherwise, don't dereference a null pointer. If you do, you'll get a segmentation fault, and your program will be dead. All right? Any questions? Yeah.
So you're not gonna have us do anything like are we even gonna have any assignments or labs that have anything to do with like, sort of like,
You will be working with pointers in assignment 3. In fact, I forget, but it could be, usually what I do is I assign, in C, I'll assign a function that you want to convert a length from metric to something else, usually to English. Well, what if you want to convert English to metric? What if you want to convert metric to, and this is why I don't use lengths, use like pressures. Pressures can be atmospheres, pascals units, PSI, right? There are lots of ways of measuring pressure, and you can convert between each one of these very, very easily. If you don't have pass by reference, that means that you can only you'd need like 16 different functions. If you've got 4 different standards, 1 to the other 3, 1, 2, 3, 1 to the other 3, 1, 2, 3. And so you'd have to have 3 times 4, 12 different functions. Or you can have one function that uses pass by reference to return 3 values. And that's usually the assignment that we give on assignment 3.
and then like for Java, you would just do some, like there would be.
Yeah, for Java, that's not possible. For Java, it's set up a little bit different that you still can only you still only have one method, but you have to pass in additional parameters to say, this is my input, gauge, I guess, is that what pressures are? Scale. Let's say, this is my input scale, this is what I want as an output scale. Now you take care of the logic in that one function. Okay? All right, I'll see you on Thursday.